So we're now going to start chapter 10, which is rotational motion. The best thing we can do is think about rotational motion as everything that we've done in terms of kinematics up until this point. So we're just going to be changing the variables, and instead of moving in three-dimensional space, we are now going to be moving in some kind of arc pattern relative to a specific point. Okay? So if I were to tell you that you started out with some angle measurement theta. So you start out with some angle measurement theta. And then in some time t, you're going to move to a new angle measurement theta 2. So you start at theta 1 and now you're going to move to theta 2. Much the same way as we talk about displacement as starting at one position, ending up at another, final position minus initial position, now we're going to go through and we're going to figure out the change in the angular motion of this object. So the change in theta. So let's go down here. The change in theta is going to be equal to theta 2 minus theta 1. Or more generally, delta theta is equal to theta final minus theta initial. So again, we're doing everything just like basic kinematics. The only difference is now we're going to be going through and dealing with thetas instead of some position in space. We are now on a position relative to a number of degrees. It's also important to point out here that all of our measurements need to be in radians. So for chapter 10, you need to be in radians. This goes for just about any problem. I think there might be a few where they ask you for degrees, in which case you have to use the conversion factor 2 pi radians in 180 degrees. Okay, and I think I have some examples coming up where we'll show that. So we've changed our displacement according to some kind of angle measure, and if we did it in some time t, then that means that we can calculate what's called angular velocity. So the number of radians that we go through per second. The number of radians that we go through per second. So omega, the Greek letter omega, which kind of looks like a nice little W, a W, is given as the angular velocity. And the angular velocity is given in radians per second. The angular velocity is given in radians per second. Now we can calculate the instantaneous angular velocity the exact same way that we calculated velocity in terms of basic kinematics. If we wanted to get the instantaneous velocity, we took the time derivative of the displacement formula, and that gives us our total velocity. Now we are going to take the time derivative of the change in theta, the change in degrees, and that will give us our angular velocity instantaneously. So to go through this, we have that omega is equal to the limit as delta t approaches infinity, or excuse me, not infinity, approaches 0, my fault, of delta theta divided by delta t. And this more generally is the time derivative of theta with respect to t. The time derivative of theta with respect to t. That'll give us our instantaneous angular velocity, and we can also get our angular acceleration by taking the derivative of the angular velocity. So to recap here, we have basic displacement where we had x final minus x initial before. Now we are doing our displacement according to some angle measurement in radians, so that's going to be theta final minus theta initial. You start at 45 degrees, you go to 60 degrees, did that ass backwards right there, but whatever. You start at 45 degrees, you go to 60 degrees, your change in the angle is 15 degrees. 15 degrees. If you're doing it in some amount of time, then we typically want to know how fast the rate of change of that displacement. So that's going to be our angular velocity, omega, and to get that we take the time derivative of our change in position according to theta with respect to time. Now we're going to do the same thing for angular acceleration. Angular acceleration is given by the Greek letter alpha. This stands for angular acceleration. And that is given in much the same way that regular acceleration in kinematics is given by meters per second squared. This is going to be given in radians per second squared. Radians per second squared. And to get our angular acceleration, we're going to take the time derivative of our angular velocity. So d omega dt. Or, the longer kind of math way of doing it, the limit as delta t approaches 0 of delta omega over delta t. Formal definition of the derivative. So if I give you a displacement in terms of angle measure with respect to time, we're going to take the derivative to get the angular velocity, and then we're going to take the derivative again to get the angular acceleration. Okay? So let's start off with a simple example. We have that theta of t is equal to 9t squared plus 3t plus 15, and we're going to assume that the angle measure is in radians. So theta of t is equal to 9t squared plus 3t plus 15, and that's given in radians. To get the angular velocity, we need to take the time derivative of that guy. So omega of t is equal to, go through a little bit of practice of some calculus here, 9t squared is going to go to 18t. The 2 comes down in front, multiplied by the 9, so this is 18t. And then the 3t goes to 3. Plus 3. And again, this is given in radians per second. Radians per second. In order to get the angular acceleration, we now take the time derivative of the angular velocity. 18t is going to go to 18. 3 is going to go to 0, because there's no t component inside there. And this is going to be given in radians per second squared. Radians per second squared. Okay? Not too bad. Not too bad. But now this is going to lead us to our 4 kinematic equations that we started this entire year with. And now we are going to transform them into their angular cousins. Okay? So the same way that we're dealing with all of our displacements in terms of angle measure, we're dealing with our angular velocity as the time derivative of that displacement, and then the angular acceleration is the time derivative of the angular velocity. Now we can go through and solve for our basic kinematic equations dealing with rotation from the kinematic equations that we learned at the beginning of the year. Okay? This may seem like you're going to have to memorize a whole lot of equations right now. But that's not the case. You are merely going to be substituting in variables. It's very straightforward, okay? So this is relating linear and rotational motion. So we're going to relate the linear motion that we've done before with the rotational motion that we're solving for now. So start out with our linear equations. We have velocity is equal to initial velocity plus the acceleration times the time. We have delta x is equal to the initial velocity times the time plus 1/2 the acceleration times the time squared. V squared, the final velocity, is equal to the initial velocity squared plus 2a times the displacement. Sorry if I'm going too fast. Give you guys a second to take a look at that. And then, one equation I can never remember, the displacement is equal to 1/2 the initial velocity plus the final velocity times the time. Okay? So those are our big 4 kinematic equations. Our big 4 kinematic equations. Now we're going to go to the rotational versions. And we're going to make substitutions because now we're dealing with new variables related to the rotational motion. Okay? So here we have final velocity, initial velocity, acceleration, and time. We're not dealing with linear velocity, we're dealing with angular velocity. So wherever you see a v, you are going to replace it with an omega. That's going to be omega. So the final angular velocity is equal to the initial angular velocity plus, now instead of linear acceleration, we need angular acceleration, which is alpha. And that's going to be alpha times t. Time is this one remaining variable that's going to stay constant here. That's all there is to it here, guys. That's it. We're just going to make substitutions inside of our linear equations for the right angular variables. Okay? I'm going to pause here for a second and give you guys time to do this. It's a good time for a coffee break, right? Okay, so now let's start off with the second equation. Delta x would go to delta theta. That's the displacement measure that we're using. V initial is once again omega initial times the time. Time has remained constant. Plus 1/2. Acceleration goes to angular acceleration, so plus 1/2 alpha t squared. Moving on to the third equation. V squared is going to go to omega squared. V naught is going to go to omega naught. And this is usually the part of the program where I make a joke that omega naught sounds like a really badass transformer. I am omega naught. If you're laughing now and listening to this with earbuds, is everybody looking at you? Or are you just not laughing? Are you laughing at me or with me? I don't know, whatever. Omega naught squared plus 2 times alpha delta theta. Acceleration went to angular acceleration alpha, delta x went to delta theta. And the final equation, delta theta is equal to 1/2 the initial angular velocity, omega naught, again, plus omega times the time. And now we have gone from the linear equations of motion to our rotational motion equations. And that's it. It seems like you need to memorize a lot here, but you don't. Do not memorize these equations. Please, do not memorize these ones over here, the rotational motion ones. You're simply going to substitute into them your angular variables.